310. Very good, so let me go further with the start. We have understood that here one can do it with an analogy of a Schrödinger equation, but it's not in advance yet. We know that one can write Schrödinger equation for this Hamiltonian, decolonize it and solve it. We want to do something more interesting, something alternative. Let's see. Let us do the following. Let us write explicitly all these multiplications, operator multiplications. Now, there's another formula. Wonder if you can swallow that. It's how operator multiplication is written in terms of integration. Nothing very complex if you recall how you multiply the matrices. So the last index of the first matrix, first index of the last matrix have to be the same. And you have to sum up over this index. That is integral expression for that. Right, so I introduce really lots of integration variables. For each side, I've introduced a separate variable xi. And I have a lot of integration. I need to take a trace after all. All right, I reconnect it. I'm back, so to see. And now I want to start to share the slides. What is this? Okay, that must be better. So multiplication of two operators is just integration, and to accomplish multiplication of that lot of something like that. No, not really. It is you introduce lots of new integration variables. You write very multi-dimensional integral, right? And since you want to make a trace, you have to make a last and first variable equal that I incorporated with this delta function. Trace of big exponent, and each w is this little exponent of a slice. Now we can do approximation on each slice, and this is a very constructive approximation one can implement. So the matrices approximately commute for thin slices. How one can prove it? Or for instance, one can just expand it in delta t and see that this formula is wrong only with the terms proportional to delta t squared. Right, let's see what we have now. We will separate our Hamiltonian into potential energy and kinetic energy. Right? Potential energy, that is simple. Kinetic energy. All right, that's what we have for kinetic energy. It is an exponent of p squared. How to deal with, how to compute this? Simplest way is to go to representation of momentum, and this operator just comes like this. It's a non-integral, it's Gaussian integral. One can take it, and the result is such an exponent. Let's see already now what it tries to do. It tries axes at different sides, at different nodes, to be equal. The minimum of this expression is achieved if they are the same. So perhaps you remember about gradient terms. It is a manifestation of gradient terms indeed, as we will see in a second. Fine. So now we collect everything and go to this model. It is still a little bit ugly because we have different variables, different nodes labeled by I. And it's just the money. Let me impose extra assumption. Let me suppose that this x is a smooth function of a node number. With that, I can approximate this difference on neighboring slides with derivative of this function. Derivative with respect to imaginary time, x dot. Now I'm ready to take the limit delta t to 0, and I end up with the following expression. Partition function is a sum over configurations. Each configuration is x, which depends on y. For historical reasons, this is called a path. So we sum up or integrate over passes. It is a path integral. This path has to be closed. Remember the delta function, which I write. So it's first point and last point got to be the same. Right. And each path comes with a Boltzmann factor. Here it is. This is obtained after, well, taking this limit. Okay, do you recognize something in this expression?
It looks again a little bit like Schrödinger, like kinetic energy plus potential energy.
That's right. It's kinetic energy. If you recall that time is imaginary, you would have it with minus sign. Okay? but we don't have any momenta and any operators of momenta. Fine. It looks very similar to Hamiltonian. It also depends on energy, but it's not quite Hamiltonian. It's something else which you don't in classical mechanics. What is that else? Yet another hint. We talked about this 2 weeks ago. Yeah. Lagrangian. Precisely. Potential energy minus kinetic energy minus because of imaginary time. So eventually it's a Lagrangian, and all right, Lagrangian doesn't have any momentum, right? Lagrangian depends on velocity. X is a dot. Fine, so the weight, Boltzmann weight for this path is determined by Lagrangian. But stress, there's no quantum mechanics in X, there's no wave function associated with X. It's just classical variable. So, to sum up, quantum mechanics can be presented as an integral over classical passes like this. That's path integral formulation of quantum mechanics. Can be useful or useless, it's one of the formulations, but there is what's important for us is exact analogy between quantum and classical. Fine. Let me approach it from another side. Let us try to get this association, this analogy from opposite direction. So we start with a classical model. Let's take one-dimensional lattice model. Right? Mostly for pedagogical reasons, I don't want to make it Eisen model from very beginning. Although Eisen model will become an application of this technique. But it looks like very much Eisen-like. It has a set of nodes in variable y, and variable x doesn't have to be plus minus. It can take any values in each node. Discrete values or continuous values. All right, so generalization of an Eisen model. Very good. Then let us try to set up Boltzmann weights, energies. Right, so there's an energy which depends on node only. Like we remember, we told about this in formulation of statistical mechanics. So we have weight W2. And we also have energy per bond, like in Eisen model, which depends on two neighboring variables. Okay, let me put it here. Very good. So how we write now partition function. It's a large integral or summation over all x's of all nodes. Yeah, we just have recently seen it when we have sliced our quantum mechanical sushi. Right? We have the sum. And now crucial thing is to recall that I can make a Schrödinger equation out of that. So I would swallow this Sochi roll slice by slice. I got till slice I. At next step, I can obtain the function by applying these two integral kernels. Bond energy and site energy. Good, so how to deal with Schrödinger equation, Schrödinger-like equation. That all we know, we just compute their eigen energies. In this case, it would be natural to call them W's. So we have a set of W's which depend on K. Looks like a mathematical exercise. The application for this is a partition function, and I would remind you that partition function is it is all what we have to know in statistical physics, right? Partition function is readily expressed through these eigenvalues. Right. The complexity of this expression depends on number of nodes we actually take into consideration. In general, with periodic boundary conditions, you have a summation over all Ks and all eigenvalues, and each eigenvalue comes with a factor of n, number of nodes. What will happen in the limit of big N? Since these eigenvalues are all different, the partition function will be dominated by the largest, highest eigenvalue. We neglect all other terms, and that's what we obtain. In other words, free energy, log of partition function per site is just kBt times log of this highest eigenvalue. Fine. Now let us compare it with quantum mechanics. That is like what we have for partition function at finite temperature. And we have to sum up it over all Ks, like in this formula. But if you go to the limit of low temperature, we can safely assume that our system is in a ground state with the smallest energy. So that partition function is just this energy, is expressed through the energy of this ground state. Right. Now suppose we can make continuous limit. Let me remind what was that in this weight. We can present it like this. Remember, it's a gradient term. It just tries to make the variable smooth with respect to I. Good. With this, we have this energy. So it's a gradient term. It's potential energy term. So in fact, what we in quantum mechanics would call kinetic energy is related to gradient jump in statistical physics. With this, we have full analogy. Oh, I forgotten to mention that this variable number of nodes is also readily transformed into the temperature. So if temperature is quantum mechanics is low, that in statistical physics corresponds to a very long system. Don't be confused. In statistical physics, temperature is finite. It never goes, it doesn't go anywhere, right? But temperature in associated quantum mechanical model, in this case, goes to 0, right? If the length of classical system is finite, in quantum mechanical formulation, that corresponds to finite temperature. Good, so we have formulated the analogy in both ways. Introduction to, I would say, methods, path integral, and what I have here is called the method of transfer matrices. Let me perhaps stress right away what is a transfer. Transfer, it's a transfer from side to side. Or in quantum terms, it is transfer in imaginary time. And this is a matrix as an exercise. Let's do it for Eigenvalue. I would like to decorate a bit the eigenvalue equation I have to solve, right? Instead of writing W2 on one side, I would spread it over the sides. The reason for that the corresponding operator is symmetric, and it's easier to diagonalize symmetric operators rather than non-symmetric ones. Good. Then I just want to fill in this matrix. So for Eigenmodel, this is 2 by 2 matrix corresponding to 2 values of spin. So there are terms related to magnetic field. There are terms related to bonds. So if I do this multiplication for 3 2 by 2 matrices, I end up with this. Right? This is 2 by 2 matrix. It has 2 eigenvalues, which can be readily computed. Here it is. We have got to the level of Ising. We have solved one-dimensional Eigenmodel. With this particular method is quantum mechanical like method of transfer matrices. Did you have it solved in your statistical mechanics course 1D Ising? Okay, I guess the method was either the same or equivalent. All right. What I will do now, at least in this transparency, I would push a little bit with quantum mechanical analogies in statistical physics. Just derive few statistical formulas which look very reminiscent to quantum mechanics. Fine, I have a statistical problem and I'm interested in the average of some function which depends on variable x on a single node. How one would compute it with transform matrix methods? Right, assuming the system is infinite, one can completely concentrate on the wave function of the ground state with the highest eigenvalue W. Here it is, and classical average is written like this. Look, surely you have seen this formula in your quantum book. It involves a squared of corresponding wave function and an operator. Let me look at more involved problem. I would like to look at the variables and two nodes separated by n bounds. Right. And this is the answer which I can derive from transform matrices. And I see here wave functions of the, so to say, excited states. And there are energies. It is very much like quantum dynamics. I have these two nodes. Let me call it I and I plus 1. And till that, let's call it time. Till that time, the wave function was in ground state. Then something happened at this node, and this is described by a matrix element of transition from the ground state to all possible excited states. So I need to invoke the function of excited state, right? And also corresponding energy. And this excited state persists till the node with this number, and then it gets to ground state again. Typical quantum mechanical construction involving transition elements to higher states, and you see that here in statistical physics. Right, I made matrix elements explicit. Right, what I would probably need is a correlation lines. The correlations persist only at the nodes which are close to each other. If you make it, if you make the distance between nodes bigger and bigger, the correlations will become smaller and smaller. And this is expressed by correlation lengths. So correlations, you'd expect it to be exponential at big separation between the nodes. All right, from that it follows, if you look at this formula, that correlation length is given by log of the ratio of the ground state let me use quantum terms, and first excited state. Good. That was just for fun to see how deep are these quantum analogies in completely classical statistics. Right, that was correlations in Eigenvalue. I put it because we can obtain that readily. We have already computed the eigenvalues, so we can write down expression very quickly. Let me look at two physical limits. First, it's a limit of zero magnetic field and low temperatures. What do you expect in this case? Suppose coupling constant favors parallel spins. Then typical configuration would look like this. There will be long domains of same spins. Then there will be something like we would call the main wall, another long domain, something like that. The smaller the temperature, the longer the domains are. Why is it so? Because it costs energy to make a domain wall. So if temperature is low, the concentration of domain walls must be exponentially small. That defines actually the length of the domain. All right, we understand, so the length diverges at small temperature, but not if there is finite magnetic field. Why is it so? Because in that case, domains won't become the same. Domain in the direction of magnetic field and opposite to magnetic field will be different, right? Will be different in length. And the correlation length will be given by the size of the most narrow domain. It won't depend on temperature. Good, that's what we understood about correlations in Eigenvalue. And let me start. It's a bit too late to start. Let me finish them. Let me conclude with an example from qubit physics. I will present it in a little bit fancy way, although it will be still a qubit, to facilitate analogies with statistical physics. Right, so let me make a qubit, and I would do it by choosing a two-well potential, like we also did for Landau Hamiltonian, and indeed it has the same structure. Two wells. So if the barriers are precisely symmetric, I will have a system of levels like this. There will be states which are mainly localized in each well, with a very small overlap, small crosstalk between them. I'd like to have kind of a qubit which I can manipulate. So I introduce extra term extra term which breaks the symmetry between two vowels. Here it is. Okay, so how will I go from this system to a qubit? Well, I would just say that I want to look at two lowest levels in each vowel. Even for the lowest levels, I will have some quantum tunneling through this barrier. Here it is. Can find it solving approximately the Schrödinger equation for this barrier. With this, I wonder if you have heard about this scheme in some classroom. Okay. Have you heard about qubits?
Why did we change from saying SU to qubits? I mean, I think qubit really the Lie algebra, the Lie group.
I don't care about algebras, I don't care about Lies. I'm just experimental physicist at the moment. And I would like to make a qubit out of materials which are in my hands. This is eventually rather practical, one of the rather practical ways to make qubits in Josephson junctions. Then we have a potential for Josephson phase, which can add quantization in this potential, quantum mechanics. You make two wells, you still have plenty of the levels which you don't need, which you don't want to use for your qubit realization. And what you can do is to concentrate on the lowest pair of levels and forget about the rest. To make simplest Hamiltonian possible, it's 2 by 2 Hamiltonian. Has two parameters, asymmetry of the vowels and tunneling between the vowels. So, if you wish, it's an analogy between how qubits are realized experimentally. Fine, all right. We diagonalize 2 by 2 matrix. Assessing energies of these qubits. We figure out that the states in the qubits are delocalized if the levels are aligned perfectly. In this case, the qubit is in superposition of left and right with the equal weights. Fine. If levels are different, if the difference of levels is much bigger than tunneling, then the qubit is either in the left well or in the right well due to big energy difference. So it is localized. Good, that's what we want to know about qubit. And now let me make, guess what? A statistical physics analogy for this ultimately elementary quantum object. I choose the underlying model for my qubit to facilitate the formulation of statistical model. Kinetic energy of the particle will become gradient term in Landau Hamiltonian. That will be potential energy, including asymmetry with respect to the wells. And if I now treat x coordinate of the particle in double well potential as magnetic field, I understand that I'm dealing with magnetization. Sorry, x is not magnetic field, it's magnetization. What is magnetic field is that parameter epsilon. Fine. So how can I find out traces of a qubit in this case? Let me look at the typical configuration for without magnetic field. As I told, there will be wide domains of approximately equal lengths, so which are separated by domain walls. What would it be in qubit picture? Okay, it goes between two levels of magnetization, which corresponds to two wells in this picture. So it corresponds to quantum tunneling in qubit scheme. And indeed, this thickness of these domain walls is what like one can get from estimating time which is spent on the tunnel barrier. And the quantum mechanical amplitude exponential is immediately related to Boltzmann weight. Right? So what stands in exponent here is domain wall energy. Right, that was without magnetic field. Let us add some magnetic field that will leave the degeneracy. First of all, how we can compute free energy in the presence of magnetic field, which is enough to compute, for instance, average magnetization. Here it is. It is given by the highest eigenvalue of transformatrix approach. Right, so we can immediately use qubit expression. That will be magnetization, next formula, average value, and indeed one could compute it with qubit wave functions if one likes to. Something else? Yeah, correlation length. These two limits again can be obtained from the difference of two eigenvalues, two qubit eigenvalues, and we can reproduce these two limits of low and high magnetic field when domains have different vectors. Okay, that was it. That was the end of analogy. Right, this system is rather simple from statistical physics point of view. This is simple from quantum mechanical point of view. So for this situation, one could proceed in both ways. In other practical situation, the system is either quantum mechanically complex and can be solved by path integral, by methods of statistical physics, or vice versa. One can use simple quantum equations to solve complex statistical physics systems. What else, as I mentioned in the beginning, is not restricted to one dimension, that can be easily extended to any dimension. It becomes a little bit complex, but anyway, it's also a method. Two-dimensional Eisen model has been solved with a rather quantum mechanical approach. Good, I'm done. Any questions? Any questions about this lecture, about the course in general? Yeah.
When should we submit the reports? After each lecture?
Good question. You don't have to submit homeworks unless you want to make an appointment for examination. You feel shocked? Are you?
A little bit. I mean,
Fine. So homework after there's some pieces of homework after this lecture. You might want to solve it, you might want to study it, it's all up to you. You don't want to control it, it's a course of your choice, all right? But if you really want to come and get a grade, okay, now it's time to check whether really you've done your homework or you study your course at all. So in order to make an appointment for examination, you have to make homework, 4 problems. One could be a problem of which you have created yourself. And you could do it alone or with another student. It's also possible to do 2 identical sets of homeworks and come together. Of course, the grade will be divided by 2, but that wouldn't shock you. Will it? Okay, just mocking. Right, and that's how we live. In addition to that, we will have some tests, right? Have you heard about tests? You?
yes.
Good, fine. So there will be tests about lecture material. I guess I will do it online. It is simpler to do it online. You get a little bit time. You get to. You are given certain time, like 1 hour, to set the results of the test. Fine. And there will be also creative problem. So you are supposed to come up with a theoretical problem of your choice. You need to find a lecturer which would be glad to evaluate your creative problem or to help perhaps this problem, right? And you have certain number of score points for this creative problem. Get this?
Is the test also part of the final grade?
Yeah, it's a part of the final grade. If you look at the bright space, it is given how many score points you get for each test for creative problem. It's all, I don't remember by heart. Let me estimate that for each test you get like perhaps 10% of your grade.
What I don't remember seeing on Brightspace is deadlines.
Deadlines for?
Homework.
Is it because,
So again, you don't have to do homework.
so it's just for
So
the
there are no
exam,
deadlines for homework.
before
There is a
the
deadline.
No, before the exam, I have
This is
to
it.
know.
There is a deadline for exam. You need to make appointment for the exam before certain date, which I guess 22nd of September, something like that. But that suggests that you would do homework by the day.
So 4 problems. 'Cause I-
Or you can find somebody to correct.
Well, I'll see.
Good. Any other questions? I'm already over my time. How did you like second lecture?
On supersymmetry.
Mhm.
I thought it was pretty interesting,
Good, good.
and it was kind of relatable to the advanced quantum mechanics course right now.
All that was, I suppose it was far more advanced
Yeah.
than my advanced quantum mechanics course. Different levels, you know. Okay, that's good. It was our new faculty member. She just started last year. I don't think that she gave any lectures. Perhaps it was her first lecture at this university. So glad to hear it was fine. Good. Thank you for your attention. See you
Thank you.
again.
Thank you for the lecture.
Thank you.